State and process. How do we define the state of a thermodynamic system? And when we change the state, how do we go from one state to another? The state of the system is described by a complete list of its properties. So for example, if we have a system and we list its temperature, pressure, and volume, then we have defined the state. If any of these properties changes, then we have changed the state of the system. So if we heat a system and its temperature goes up, that's the change of state. If we compress the system and its pressure goes up, that is another example of a change of state. The process is what the term we use to describe the change of a system from one state to another. So heating, cooling, compression, expansion, these are all different processes that we will be studying. How do we graphically depict a thermodynamic process? If we are going to show this on a two-dimensional graph, then we need to select two properties and show the relationship between them on the graph. Now we can select any two properties, and that depends on the process and what is most convenient for us in analyzing that process. So as an example, let us look at the compression of a gas. This is a cylinder which contains a gas, and there is a piston which is compressing the gas. The two most convenient properties are the pressure, which we can measure using a pressure gauge, and the volume, which we know if we know the position of the piston. So the graph that we will draw will be the relationship between the pressure and the volume. We can mark the initial state, which we're calling state 1, where we know the pressure P1 and the volume V1. The piston then moves and we reach the final state, state 2, and there again we measure the pressure and the volume P2 and V2. If we know the intermediate stages between state 1 and state 2, then we can mark them and draw what is known as a process path. This gives us what is known as a PV diagram for the process. Now, there are several processes which are important in which one property is held constant. One very important type of process is what is known as the isothermal process, in which the temperature of the system is constant during the process. So if we want to compress this gas in an isothermal process, we could put a constant temperature water bath around it, and the water will force the gas to be at the same temperature as the water. So while we compress it, the gas will lose heat to the surrounding water, and the temperature of the gas will be constant. A different type of process is what is known as an adiabatic process. And this is one in which there's no heat transfer to or from the system. Now we can do that by putting an insulation around the cylinder, and we assume that this is a perfect insulation so that there is no heat lost. Now, while we compress the gas, the temperature of the gas will go up because the work done during compression increases the energy of the gas. Now, it's important to remember that adiabatic and isothermal refer to very different processes. The first, adiabatic, is one in which there is no heat transfer. The second, isothermal, there is heat transfer, but the temperature of the system remains constant. Another term that we are going to be using is that of an adiabatic wall. And this is a wall which is a perfect insulator and does not allow any heat to cross it. An isobaric process is one in which the pressure of the system is constant. So if we take our gas in the cylinder and we heat it, if the piston is free to move, then the pressure of the gas must always equal the pressure of the atmosphere. So as we heat it, the gas will expand, and the pressure will always be constant and equal to the pressure of the atmosphere. Now, if we want to do this expansion at a higher pressure, we can keep a weight on the piston. So the pressure of the gas now has to support both the atmospheric pressure outside as well as the weight of the piston. And so therefore we can select any pressure that we want by selecting the weight that we put on top of the piston. An isochoric process is one in which the volume of the system is constant. So we put the gas in a rigid container whose volume does not change. Now, when we heat up the gas, both the pressure and the temperature of the gas will increase, but the volume will remain constant. Over here we have a piston which rapidly compresses the gas confined in the cylinder. And the question is, can we measure the variation of gas pressure as a function of volume? Now, at first glance, it might seem fairly obvious. Yes, we can by putting a pressure gauge. But think about this a little more closely. So when we are compressing the gas, if we think of the gas as being composed of molecules, the molecules don't have time to move away from the piston, which is moving very rapidly. So therefore, you get molecules accumulating near the piston, and therefore you actually have a high pressure near the piston. During an expansion, you got the reverse happening. The piston is moving away very rapidly and it has few molecules next to it, and so therefore you have a low pressure near the piston. It is only when you reach a state of equilibrium that the molecules are able to move around and distribute themselves uniformly. And then you have a uniform pressure everywhere inside the gas. So therefore, it is only when you have a state of equilibrium that it even makes sense to talk about a system pressure. Because if the piston is moving and you got a pressure gradient inside the gas, where the pressure is higher on one side and the pressure is lower on the other, then there's no single gas pressure or a system pressure we can talk about. It is only in a system that is at equilibrium that we can define a system pressure. So now this raises the question is, how do we define a process path while the piston is moving? So over here, the piston is stationary, the gas is at equilibrium, and we mark both the pressure and the volume. Now the piston moves by a small amount, so the volume reduces by delta V. We wait until the gas again reaches equilibrium, where we can measure the pressure and the volume, and we mark that on our graph. And we repeat this process, each time moving the piston by delta V. And we finally get a series of points, and each point over here is an equilibrium state, so we can define the pressure. Now, if we reduce delta V, we'll get a larger number of points, and we'll be able to better define the path. And in the limit that delta V goes to 0, we can draw a continuous line between the initial state 1 and the final state 2. This path is what is known as a quasi-equilibrium process. Every point along this path represents an equilibrium state where we can define the system properties. And it's important to understand that when we draw a process, we are implicitly assuming that it is quasi-equilibrium, and we can therefore define the properties at every stage along that process. Let's talk about processes which involve heating or cooling. And to do that, it's useful to define what is known as a thermal reservoir. A thermal reservoir is a system whose temperature remains constant despite heat transfer to it or from it. Examples would be the atmosphere or a lake. So you can add heat to the atmosphere, but it doesn't really change the temperature of the atmosphere. In practice, any body that has a very large thermal mass compared to the heat transfer to it or from it is a good approximation of a thermal reservoir. So We have over here a thermal reservoir which is at some temperature T1. Now we have another one which is at a slightly higher temperature T1 plus delta T, and one which is even higher at T1 plus 2 delta T, and so on until we finally get to a temperature T2. So we got a whole series of these thermal reservoirs. Now we want to heat up this system from temperature T1 to temperature T2. We bring it in contact with the first thermal reservoir, which is at T1. Now, initially, the system would have a temperature gradient within it. The temperature will be higher where it's in contact with the thermal reservoir, and it'll be lower on the other side. But if we wait long enough, the system will come at equilibrium, and then the temperature everywhere will be uniform at T1. And we can therefore then define a system temperature T1. Now we replace the thermal reservoir with the next one, which is at T1 plus delta T, and then the next one, and so on until we've reached temperature T2. So we've heated the system up from T1 to T2, and we've gone through a series of temperature which each state is an equilibrium state where we could define the system temperature. In the limit that delta T goes to 0, we have quasi-equilibrium heat transfer. Now, again, it's important to realize that no real process is quasi-equilibrium, but we will see that this is a very useful approximation which we can use in thermodynamics to define different processes. A thermodynamic cycle is any process or series of processes that result in the system being restored to its initial state. So here we start compressing from our initial state P1, V1. The piston compresses, but then it expands. So now if we draw the process, we actually have two overlapping processes, one which goes from 1 to 2, and the other which goes from 2 to 1. If we want to evaluate the change in volume, delta V, during this process, we can integrate dV, and we'll do it for the two separate processes. The first one from 1 to 2, so we integrate from V1 to V2, and the second one is from 2 to 1, so we integrate from V2 to V1. If we evaluate the integral, we get V2 minus V1 plus V1 minus V2, and that adds up to 0. So for this cycle, delta V is equal to 0. Now we could have a more complicated cycle. So this is a cycle which consists of 4 processes. There's a constant pressure process from 1 to 2, and we could do that by cooling the system. 2 to 3 is a compression process. 3 to 4 is another constant pressure process, which we could do by heating the system. And finally, we could expand the system from 4 to 1. If we want to find out delta V, we can integrate dV for each one of these processes from 1 to 2, from 2 to 3, 3 to 4, and then back from 4 to 1. And if we evaluate that, delta V is equal to 0. This leads us to the conclusion that the integral of any property x, if we integrate it over a cycle, equals 0. And this is an important observation because it also serves as a test for us. If we want to check if any quantity is a property, if we evaluate it over a cycle and it's equal to 0, that means it is a property. We can write this mathematically as the integral dx equals 0, where the symbol of the integral sign with a circle through it means it's an integral over a cycle. To summarize, the state of the system is described by a complete list of its properties. A process is when the system changes from one state to another. A quasi-equilibrium process is one where the changes are infinitesimally small, so that every stage is an equilibrium state. And finally, a cycle. Any process or series of processes that result in the system being restored to its initial state.